Hello students, in this video let us discuss problems applying inverse Laplace transform. In this video we are discussing two types. One type is by completing square procedure. Another type is you are finding inverse Laplace transform of logarithmic function and inverse trigonometric function. So two properties we are using. Let's see first how to solve inverse Laplace transform by completing square, and for this which property is applied. We know that first shifting property defined by L of e power at into f of t is f of s minus a. If you apply inverse Laplace transform on both the side, we get inverse Laplace transform of f of s minus a will be e power at into f of t. So we know that inverse Laplace transform applied on s term, it gives us t term. So this can be written as e power at f of t nothing but what? Inverse Laplace transform of f of s. When it is applied. For example, we know that inverse Laplace transform of 1 by s minus a is e power at. But if we have the problem finding inverse Laplace transform of 1 by s minus a whole cube or whole square or whole power 4 or whole power 5, so on. So you cannot obtain directly the applying the formula. We don't have any formula for s minus a power. We have only formula for s minus a in the denominator. So here the shifting property can be applied. How? If you replace s minus a to s, it is easy to obtain the result. Inverse Laplace transform of 1 by s cube, you know that. So this is considered f of s minus a. This is considered f of s minus a. You are finding inverse Laplace transform of f of s minus a. The result will be, shifting property always contain exponential e power at, right? So we write exponential. What is the a value observing? Here it's a general form I am taken, e power at inverse Laplace transform c e power at inverse Laplace transform of f of s, means you are shifting s minus a to s. So we are shifting s minus a to s in our problem. It is 1 by s cube. Then you know that how to apply, write the result of inverse Laplace transform of 1 by s cube. It is what? T square into 2 factorial. Similarly, let us discuss another example like inverse Laplace transform of, we have like this, s plus 2 whole square plus 1, s plus 2 whole square plus 1. See, here also when you shift s plus 2 to s, we get the standard format of s square plus a square. Therefore, we have to shift. Here we can apply the shifting property. I am explaining when to apply the shifting property. I will come to the procedure of completing square when you are solving the problem. So now we have to shift s plus 2 to s, right? So while you are shifting s plus 2 to s, we observe it is s minus a format. S minus a format. You are shifting s minus a to s, means a is minus 2. So therefore our result become e power minus 2t. Inverse Laplace transform of f of s, means you are shifting s plus 2 to s, s square plus 1. Then the result is e power minus 2t. It is 1 by s square plus 1 is sin t. When the numerator is not s term, this is how you have to solve. Suppose the same problem, if we have s plus 2 whole square plus 1 in the numerator, but s is there in the, s plus 2 whole square plus 1 in the denominator, s is in the numerator. Here, very important, if you have denominator is s plus 2 format, the numerator s is also should be same format. So how can we change? Just you add it 2 and subtract 2. So just you make it, yes, if you have s term in the numerator, it should be the same format of denominator. Now shifting s plus 2 to s means you are applying shifting property. A is minus 2, e power minus 2t. Then inverse Laplace transform of s minus 2, where all we have s plus 2, that is changing as s square plus 1. Next, this can be written as e power minus 2t, inverse Laplace transform of s by s square plus 1, that is cos t, and inverse Laplace transform of 2 by s square plus 1 with minus 2 sin t. This is how we can apply the shifting property. Now let's solve the problem by completing square and applying shifting property. See the denominator. So let us check. This denominator can be factorized. If it is factorized, you can apply the partial fraction method that is explained in the last video. This cannot be factorized. So what you can do, we have to take this is completing square format. Means we have to take a plus b whole square or a minus b whole square. So from s square you will clear that it is a square. Next, because of this minus sign, we analyze it is a minus 2ab format. So minus 2 into a is what? S. B. To get this minus 4s, b must be 2, because you will not get the same minus 4s. So b must be 2. So I'll take 2. Then b square is 4. Then from 13, if you subtract 4, so remaining will be 9. So this is what completing square procedure. Then this can be written as s minus 2, a minus b whole square, that is s minus 2 whole square plus 9. So the given problem can be written as s plus 2 divided by s minus 2 whole square plus 9. So from this, here you can apply the shifting property. But before that, let us observe. Always we observe the denominator. If you shift s minus 2 to s, it becomes s square plus a square format. And now we observe that numerator is containing any s. Yes, we have the s term in numerator. We should make it a same format of denominator s minus 2. For that, so we write this as L inverse of s minus 2 plus 2 and another plus 2 we have here plus 4. This doesn't change our original function. So it gives the same. S minus 2 whole square in the denominator plus 9. Now you can apply the shifting property. So what shifting property says? It is e power at L inverse of f of s. So what is a here? 2. So our answer is e power 2t L inverse. You are shifting s minus 2 to s. So that is s plus 4 divided by s square plus 9. Next, we separate it. E power 2t L inverse of s by s square plus 9. It is what? Cos 3t. We have s square plus 9 is what? S square plus 3 square. So you can write this as s square plus 3 square. Next, we have L inverse of what? 4 by s square plus 9. So we keep 4 out. Then it will be 1 divided by s square plus 9. If there is no s in numerator, a should be present. What is our a? Area 3 square. A is 3. So we multiply and divide by 3. So what we get? 4 by 3 sin 3t. Let's solve now inverse Laplace transform of logarithmic functions and inverse trigonometric functions. To find inverse Laplace transform of inverse trigonometric function or log function, we apply the property that you have studied, that is Laplace transform of t into f of t. Laplace transform of t into f of t. Second property, multiplication by t. So here this is defined by what? Minus 1 power n, where n is 1. So minus d by ds of f of s, where f of s is what? Laplace transform of f of t. So now, how we are applying this property in our problem, inverse Laplace transform of inverse trigonometric function or log function. From this property you can write this can be rewritten as minus f dash s. So d by ds of f of s in other notation format can be written as f dash s. Okay, d by ds is a differentiation f of s. So f dash s also one first differentiation of with respect to s. So now, so inverse Laplace transform of f dash s can be written as inverse Laplace transform of f dash s can be written as, so shifting minus to the other side, so we get minus t into f of t. Just you observe, applying inverse Laplace transform on both the side. L inverse L become cancel, so we get t f of t in the left side of what we have the step previously. Right side we have minus f dash s. Okay, so minus I taken to the other side, I am applying inverse Laplace transform on f dash s. So this property we are applying to find the inverse Laplace transform of inverse trigonometric function and log function. You can easily identify when in the exam, if they are given inverse trigonometric function, only two functions they will ask you, tan inverse or cot inverse. Or log function, we have to apply this property. Because why f dash s? Because we don't have Laplace transform of any log function standard result. Okay, Laplace transform of inverse transform result. We have, suppose for example, we have log s plus 1. So we don't have Laplace transform of log s plus 1. But if you differentiate log s plus 1, differentiate log s plus 1, it will be 1 over s plus 1. Okay, if differentiating log of s plus 1, it will be 1 over s plus 1. So then that is differentiation. What we have here, f dash s. Okay, so suppose your f of s is log s plus 1. Can you find inverse Laplace transform of log s plus 1? Because we don't, it is not possible because we don't have any standard result. Okay, in this case what we are doing, we are differentiating this, that is f dash s. We are differentiating this. So what is differentiation of log s plus 1? It is 1 by s plus 1. Now you can find easily inverse Laplace transform of 1 by s plus 1. Right? So that is inverse Laplace transform of f dash s is inverse Laplace transform of 1 over s plus 1. So according to the property that is we are discussed now, this one. So inverse Laplace transform of f dash s is what? Minus t f of t. Minus t f of t. So right side we know that inverse Laplace transform of 1 over s minus a is what? E power a t. So it will be e power minus t. So finally our required result is what is f of t? Given f of s. Given f of s, inverse Laplace transform of f of s is what? F of t. So given finally our required result should be f of t. From this you can write the result is minus e power minus t divided by t. So taking this minus here and dividing this t here, so we get the final result in this way. This is just a simple example I took to convince you. So we have the problem now. F of s given that log of s plus a divided by s plus b. This is given in the question paper. So let us see that immediately you will come to know this is a log function. This is having different procedure compared to so far what you have done, previously what you have done. Previously we have not differentiated any function, but we don't have any standard result of log and inverse trigonometric function. We have to differentiate this. By differentiating, you could obtain the inverse Laplace transform. Okay. First, let us differentiate both the side with respect to s. Differentiate with respect to s both the sides. Okay. So left side f of s we have by differentiating. So by notation format, I'll write it is f dash s. By differentiating f of s, it gives us f dash s. And before differentiating, all the times whenever log function given, see that a property of log can be applied, then it will be simple to differentiate, integrate, whatever. Okay. So first we do that. I forgot to tell. So first log function given, let us see that property of log can be applied. Then we go for differentiating. Now we have the format is what? Log m by n. So can be written as log s plus a minus log s minus b. Sorry, s plus b. Now this is easy for differentiation also. Okay. So therefore f dash s log s plus a differentiation is 1 by s plus a. Next minus log s plus b differentiation is 1 by s plus b. So now just you confirm it, can you obtain the inverse Laplace transform of 1 by s plus a? Yes, right? So now you take inverse Laplace transform on both the sides. Once you are confirming RHS is in the standard format of applying inverse Laplace transform, we apply inverse Laplace transform on both the sides. So inverse Laplace transform of f dash s. Inverse Laplace transform of f dash s is right side I'll take inverse Laplace transform of 1 by s plus a minus inverse Laplace transform of 1 by s plus b. Okay. So then according to the formula we have discussed okay, it is minus t f of t. That you have to remember. Don't forget minus there. Okay, minus t f of t. Right side it is in standard format. So 1 over s minus a. Since it is plus, we have to write it as e power minus at minus e power minus bt. So finally we are writing the result. Required result is always what is f of t. What is f of t? That is just we are dividing by minus t in the RHS, f of t coefficient. So because of minus sign I can write here e power minus bt first. Next minus e power minus at divide by t. So next problem, log of 1 minus a square by s square. So given f of s is log of 1 minus a square divided by s square. So we are solving inverse Laplace transform of log of 1 minus a square by s square. First let us simplify. This can be written as log taking s square is a LCM. So it is s square minus a square. S square minus a square. Then it is in the form of log m by n, can be splitted as. So you can write f of s as log of s square minus a square. Log of s square minus a square minus log s square, that can also be written as in simple form 2 log s. We differentiate both the side with respect to s. So differentiating with respect to s both the side, differentiating with respect to s, we get f dash s. So log function, we are differentiating log function. It is 1 by the function, 1 over the function, and differentiation of the function is 2s minus differentiation of keeping 2 as it is, log s is 1 by s. Inverse Laplace transform, applying inverse Laplace transform on both the sides. So inverse Laplace transform of f dash s is what? Minus t into f of t, and 2 inverse Laplace. So this is our result. So the problem is find inverse Laplace transform of log of s square plus 1 divided by s into s plus 1. So the given function can be written as f of s is log of s square plus 1 minus log s minus log of s plus 1. Next we differentiate both the side, differentiating both the side with respect to s, we get left side f dash s, right side 1 divided by s square plus 1 into 2s So log function differentiation minus 1 by s minus 1 by s plus 1. Next we apply inverse Laplace transform on both the sides. Inverse Laplace transform on both the sides. We get left side minus t into f of t. Right side based on the formula 2 keeping out s divided by s square plus 1. It is a standard form, writing as cos t minus 1 by s 1 minus e power minus t. So finally our result f of t. Our result is f of t. It is including minus sign. I'll take 1 plus e power minus t minus 2 cos t divided by t. Find inverse Laplace transform of f of s is cot inverse s by a. Cot inverse s by a. First we differentiate both the side with respect to s. It gives us f dash s in left, right side cot inverse x. It is minus 1 by 1 plus x square. Here we have s by a, s square by a square. Also we have to differentiate this s by a, where s is a variable. So s by a is what? 1 by a. 1 by a. Now we simplify this. Before applying inverse Laplace transform, let us simplify this. So what you can do simplification here? We take s square plus a square divide by a square, and that goes to the numerator. Taking LCM in the denominator here. So 1 plus s square by a square is there, no? We take a square is the LCM. This we get a square plus s square. That is I am written in order s square plus a square. Okay. That what happens? Divide by a square is there, no? This divide by a square after taking LCM. That goes to the numerator. That is what written here, a square divided by s square plus a square. And also we write it is there is 1 by a. There is 1 by a. Now a gets cancels. A gets cancelled. We have now a divided by s square plus a square. Okay. Now we confirm it. Here you can apply inverse Laplace transform. Next further simplification doesn't required here. So now operate inverse Laplace transform on both the sides. Inverse Laplace transform on both the sides. So that gives what? Minus t f of t. Minus t f of t. Right side also we have minus. Inverse Laplace transform of a by s square plus a square. We are operating inverse Laplace transform on both the sides. So just for your convenience I am writing inverse Laplace transform symbol there. Doesn't required also. Okay. So now both the side minus gets cancelled. This minus gets cancelled. Okay. Finally our result. This can be what? This can be written as what? Sin at. Because a is present in the numerator, sin at. So finally our required result is f of t is the answer, sin at divided by t.